Auchikona uchina kokova. Iwe koko, auchikona uchina kokova. Kokova, iwe kokova. Koko, auchikona uchina kokova. Kokova, iwe kokova.
Baby tazuni chisiro Sumbusa mwana Gurasa unumutimo Sumbusa mwana Mariangu tali wangu Dorone nyama yangu Nikoga upenyu kangwi
Africa, uchikona uchina kokova. Africa, Africa, Africa. Iwe Africa, uchikona uchina kokova. Africa, Africa, Africa. Nani Zimbabwe, uchikona uchina kokova. Zimbabwe, Zimbabwe, Zimbabwe.
Hello, everyone. Nice to see everyone here. I see about like 47 attendees. Nice to see everyone here. Thank you for joining today's session. Today we're going to be looking at pandas and NumPy. I am your host for today. I'm new. I don't think you have seen me before. I see a hand raised. I'm not sure if that's okay, got it. So yeah, so I'm new to the data program. Here we have also Segun, Bali, Byron, and John. I think you already are familiar with them, but maybe not from me. I'm Leikun. I'm a technical mentor here in ALX. Previously used to support the SE, the software engineering tracks, front-end, back-end, product programs. Some of you may have taken some of those programs. You may have interacted with me, I'm not sure. However, today I'm just going to be holding this session with you guys on NumPy and Pandas. Yeah, it's really nice to see you guys here. I just want to know if everybody can hear my voice clearly. Should I raise my voice up or down? Is everything okay? Can you see the screen? Is the connection okay on your side? Everything's cool? Thumbs up or down? No? Okay. I see Gulma says, okay, perfect, awesome. Okay. So yeah, today's agenda is we're going to go through the rules of engagement first, going to the main session. We will have a Q&A and updates and announcements at the end. So yeah, let's get started. So if you have any sort of questions, we do have Q&A. This is a webinar, Zoom webinar, so we do have a Q&A, so you can put it there, and every now and then I can jump in there and see your questions and answer it as best I can. Feel free to use the chat library and respectfully as well, liberally and respectfully. We'll be opening it an ad hoc thoughtful sessions, and listen, learn, and engage. Yeah, these are the rules of engagement for today's session. Okay, let's go ahead. So I think I have already introduced myself. Leikun, I'm a software engineer, first and foremost. I do have enough knowledge about Python, but my tech stack currently is on Node.js, TypeScript. For the front-end side, I do some React, but mostly I use Next.js. On the back-end side, I'm more of a Nest.js person, coming from the Java Do you hear me? I think you
Yeah,
should
now
hear
we
me
can
now.
hear you.
Awesome. Awesome. I'm sorry about that. It was VPN related issue. Sorry. All right. So we're going to go through understanding and applying the core functionalities of NumPy and Pandas for data analysis. We're going to use an example data from, we're going to pull it from somewhere. It's going to be about like the Titanic survivors and stuff like that. It's quite interesting. All right. So this is not actually, this is a previous slide. So ours is going to be different. It's going to be on the Titanic survivors, the data set. This is an old data set. I think the slide was not updated, that's why. Okay, so let's dive into the today's agenda. Let me see. All right. Let me open up the, all right, so this is the one, I think. Yeah, awesome. All right, so as I said, we're going to start with NumPy and move on to Pandas. And if we can make some time, we're going to see an example, the example data set I told you about, the Titanic passenger records. You can find this one. So I'll be sharing this workbook itself with you guys. I'll push you to GitHub or somewhere that's convenient for you guys to pull it from. So the data set is the Titanic passenger record. So let's see what it contains first. So let's open the new tab here. Right, okay, so it's a CSV. Currently you may not actually see it clearly. So so whether the person survived, the peak class, the sex, the age, all the columns are here. So this is where we're going to be manipulating it using both NumPy, actually Pandas. We're going to start with NumPy just to understand Pandas, because as you guys may know already, Pandas is actually built on top of NumPy, right? So yeah, we can start with that. All right. Okay, so why does NumPy actually exist? So Python lists are very flexible. So previously you should have learned or known about the different data structures Python has to offer. For one of those data structures is a list data structure. It's quite flexible. You can use multiple elements and group them together into a list. So Python is quite different from other programming languages, even though it's you know, a normal programming language that you can use for software engineering purposes. It's actually built to be very universal in how it handles multiple data. So, for example, for languages like C or C++, or even Java, when you create something that looks like a group set of in a group set, it has to be either an integer or some type of a data type. That's not the case for Python. You can put in a list whatever you want. It could be a string, it could be a floating point number, it could be a simple integer. It can be also an object or another list as well, can be grouped together within one Python list. So it's very flexible. So they actually hold integers, strings, and even other types of lists within the same container, right? So this flexibility has a hidden cost. Python is an interpreted language. So mixing these together, it doesn't actually allow you to use contiguous memory. Instead, it's going to be scattered in your random access memory, and you'd have to sift through each one of those scattered memory areas in your random access memory, and you know, that is going to be very costly, right? So every element is stored as a separate Python object in memory. So each carrying type information, reference, and counts and padding. So it's quite large. So it's not everything is going to be stored as an object. So when you first, for example, here compute um, this list comprehension, you guys should already know what list comprehensions are. Who can tell me like what list comprehensions actually allow you to do? Maybe let me open it up for everybody here. You can use the chat. So this is a list comprehension, right? So what do you think this one does, maybe? Anybody on the chat? Yeah, exactly, right? Yeah, multiply, double X. So you have a million items, right? So this is going to be kind of like a number that multiplies each item in the list by 2. Exactly. So for X in million items, this could be some kind of a range, right? And for each one of them, you multiply each of those elements by 2 and create a new list out of that, right? Range itself is kind of like an iterator. It's not exactly a list, but it's an iterator, right? So you're going to create something off of that. So when it does this in Python, so it fetches each object from potentially non-contiguous memory. What this means exactly is, so if you think of your memory like boxes stacked side by side, right? So in a normal way, like when you create lists in other languages, they would be put in contiguous memory areas, like side by side, right? That's how they would be put. However, in Python, that's not the case, right? Those objects would be living in different parts of your memory, but the references of those memories or the address to those memory areas will be stored in the list, right? So doing this calculation itself will actually take much more time than expected. So it's very, Python for loops are very slow compared to other languages. Um, on top of that, Python is kind of like the second to last language in the like in the speed leaderboard, right? So the very last one is Ruby. If you guys know that language, I'm not sure. Ruby is very slow. It's slower than Python. Python is just next after that, right? So yeah. Um, so it checks its type then, right? It dispatches to the integer multiplication method, which is this exactly when it tries to multiply it. So it has to check the type first before multiplying that entity. If it's a number, it multiplies it by 2. If it's not a number, it's going to be like a string type of interpolation, right? And allocate a new Python object for every result, right? That's how Python takes care of this type of list comprehension. So I'm trying to build you up into like why we need NumPy, right? Okay, so for a million items, let's say this one, there's going to be a million type checks, a million method calls, right? So multiplication method, and a million allocations. These need to be performed first. So all of them are going to be in a slow interpreted loop. So the for loop exactly right here, right? So what NumPy does is it solves this with ND array or n-dimensional array. So dimensionality means like, um, so for example, if you have a list of lists nested within, that's going to be two-dimensional. If you only have one list, then that's going to be one-dimensional. But you can create many dimensions also, 3 or 4, even more than that, right? Yeah. So every element in NumPy's ND array is of the same type, right? And stored in a single contiguous block of C memory. So this might be a little bit confusing. What is C memory? Well, C is a language itself. So Python, if you, for those of you guys who don't know, Python, the normal Python that you find when you go to python.org and download it from there. All right, so if you go to downloads here and you download Python, this particular version of Python is actually written with the C programming language. So C is an old higher level programming language, for those of you who don't know it. And Python is built on top of it. So C is used to build Python, right? So what actually makes that interesting is that you can actually write C level code and integrate that into Python and then have the speed of the C programming language work inside of your Python programs, right? So that's what basically happens, right? Like NumPy is a bunch of C functions, C methods that actually speed up your process of doing these types of calculations in Python, right? The reason that they're doing that is because Python itself is a very, very simple language, but it's very slow. But it's also written in C. So why not leverage C to actually make it faster? So that's the whole idea. So here what happens is, um, so no Python overhead per element, right? So this doesn't happen. So all of these calls are just going to be omitted and C is going to be handling all of this stuff. All right. Let me just check one thing. All right. Yeah. And operation calls like precompiled BLAS and LAPACK routines that these run at native machine speed because these are basically going to be run in the C environment, right? So Python is not going to be responsible for this. So yeah, that's what basically happens. So the ND array, what you can think of it in ND arrays are, for example, if you have a 1D array here, and the shape of it is of 5, then this is how um, you would see it, right? So this is a one-dimensional array. 2D is going to be like shape of 3 and 2, right? So always the first one is going to be the row count. So row counts are these higher level lists or arrays, as you can see. These are the rows. And then the second one is going to denote the number of columns, which you can count this way, right? So that's basically what it is. So every array has 4 key attributes in NumPy. So it's the D type, which is basically the data type of every element. So it could be like a floating point, a 64-bit floating point, which basically means a decimal number, an integer, a 64-bit integer, which also means a number, but it's not decimal, and a Boolean that's just 0 or 1 or true or false, right? That's the data type. As I said, you cannot actually combine multiple data types in one array, right? And in one ND array. If you start with number, everything has to be a number. If you start with a floating point number, it has to be all of the elements have to be floating point. All right. The second one is the shape or the size in each dimension, right? So basically in the first one, we have the size is 5. In the second one, you kind of just give it one number. It has to be two numbers because you have rows and columns, right? So for example, 10 rows and 2 columns. That's how you would read this one. And number of dimensions also is part of it. So for a 2D array, it's going to be 2, right? And then the size, the total element count, in this case, you have to multiply the row count with the column count. It's going to be 20, right? So these are the attributes of each ND array that you create in NumPy, right? So NumPy, the underlying implementation of NumPy is C, right? C is going to be handling it. And in the C programming language, you're not allowed to create an array that has multiple data types. It's only that's the limitation that has spun up to the NumPy package, and you cannot use like multiple um, data types within a single ND array. I hope that's clear, right? So that's just like the why of NumPy. Okay, so just to demonstrate like the speed difference between a simple Python list, we're going to fill everything with only numbers just to make things easier for Python, right? We're going to start with that and also create a NumPy array with the same size and then compare the list comprehension speeds between the two, right? So that's what we're going to do here. So let's read on the code here. So you have to install NumPy first and import NumPy this way. So you can straight up use NumPy as is, but you can also map it to some other name, NP. You can use it as this or as NP. Then in which case you have to use NP every time you want to create or you want to use NumPy, right? Okay, so let's start off with the first line of code here. So this is a size, which is just a million. This is just a number. We want to create a Python list as well as a NumPy array using this size, right? So this is 1 million. This underscore, you should know by now, you can do this in Python, not in any other language. I'm sure there is this type of writing in JavaScript as well, but don't quote me. But you can write numbers this way, and Python is smart enough to identify these don't mean actually underscores, and they're just separators, right? These are here only for your eyes, okay? Just for the human eye. This is just going to be interpreted internally as a 1 million. So yeah. Okay, so let's create a Python list. How do you create a Python list? You just use list, and then you give it the size using range, in which case the memory will be allocated for a million arrays, sorry, a million elements in one list in Python. Okay, then we also have time, as you can see here. We're going to try to timer this. And what we want to do is do the same thing I showed you earlier, which is create a different array off of this by multiplying each element by the number 2, right? So x multiplied by 2 for every x in PyList. PyList is the list that we just created above here, right? So this should create a result list. It's a different list from the first one. Those two are not the same, okay? These two are different, but the second one is actually derived from the first one, all right? Once we finish, we time ourselves and see the output. Okay, so this is the list time and this is the NumPy time. When you try to create a NumPy array with the same size, it's quite straightforward. It's not as as complex as creating a list in Python. It's very straightforward. What you do is you use NP and then create a range with this size, right? In which case you have a NumPy array, right? And then you go on to just multiply that same array with 2. Now, there's a difference between this way of doing it and in list, as you can see, right? What we're doing here is we're creating a separately new list, right? And multiplying each element by 2. And then that's what we're saving as the result list. In NumPy is actually smart enough for it to know that we don't want to multiply the list itself. Instead, we want each element inside of the list to be multiplied by 2, right? So this is how you would do it. It's quite hard for someone who just knows Python to jump on NumPy and understand this because in Python, it's not the same, right? So if I do this, for example, let's add one cell below here. Let's say I have a list of 1 and 2, right? So I can just print the list here. So let's play this one. So the list is 1 and 2, right? So what happens is, like, if I multiply this by 2 and run it, as you can see, it's not as I expected, right? What it did was it created a separately new list, right? This is the new list, and it duplicated all the elements I have inside, right? This is not useful for most of our cases, for especially for data analysis and all that data stuff, right? Instead, we want a simpler form of multiplying each element by two, instead of creating a separately new list using Python, right? So we don't want to do that. So let's just delete this one. All right. So we multiply that by two, and then we again time ourselves. Now let's see what the outcome is going to be. So the Python list version of the time is so list time to 4 decimal points of precision. This is going to be in, I think, seconds. Yeah, it has to be in seconds. And this one also the same. So we're going to see how much faster NumPy is, at least in my system, right? So let's see. Let's run this one. All right, so the Python list took it about 0.016 seconds. The NumPy list took it about 0.0012 seconds, right? So if you calculate this, you get about like 13x fast, right? So this is orders of magnitude faster than Python, right? It's very fast, 13 times faster. You can imagine like if you took to process um, a list in Python, let's say, um, no, in NumPy, if it took you 1 minute to process a list like this, in Python, it would take you about 13 minutes, right? If you take that into 1 hour, if it takes you 1 hour to process a list in Python, in NumPy, if it took you 1 hour, in Python, it would take you 13 hours, almost like half a day, right? So when the data set gets bigger and bigger, the amount of time is going to be much more significant, especially the difference between the two, right? Right now, it might seem very fast. Python is fast, of course. As you can see, it's like in milliseconds, right? Like it's very fast. But when the data grows is where you actually see the difference. Okay, I hope this made you appreciate like how NumPy is greater than the built-in Python lists, right? Okay, so how do you create arrays? So there's 5 key functions in NumPy that allow you to create arrays, NumPy arrays, basically, right? So in Python, in the normal Python language, you don't get like an easier way to generate a list with built-in numbers, right? Or you want them to be like stepped values. You would have to have like multiple lines of code below the creation of the list itself to be able to like populate that that Python list. However, in NumPy, you have many ways of creating this. They're very convenient. So the first one is just the one that we saw earlier, which is mp.array, and then you give it any type of list. This can come from either a CSV value that you are pulling in from somewhere else. It could also be an API call. Most of the time, you pull data from an API, an external service that's out there. You connect to it via its web server, and then you download it, or you instead of downloading it, you put it straight into your NumPy array, right? So this can come from anywhere, right? So when you want to create it using Python list, you can do it also, but it can come from anywhere. The next one is mp.zeros. This is very important. It creates the array, but also it initializes every element with a specific value. In this case, it's going to be 0, right? So when you need a blank array to fill later on, maybe. And with ones also, so pre-filled with ones, with a shape. Shape is basically the size of the array. We talked about this earlier. You have a range, so MP a range. there's a start, a stop, and a step value. When you need evenly spaced values with a known step size. So for example, you want to start from 0 and you want to end up at 10, but you want to have a step of 2, in which case you only have 5 elements, right? You start at 0, sort of 6 actually, 0 is going to be included, 0, 2, 4, 6, 8, and 10, right? Yeah, and the last one is linspace. So this is when you need a precise count of evenly spaced values. So the problem with the first one, which is um, arrange, um, the problem with this one is the last one will not be included, the stop value, right? In the newly created array, the stop value will not be part of the array. And also because of that, you wouldn't be like inclined to use it if you want perfect steps and you want both sides of the bracket to contain the least and the most values. However, when you use linspace, you are guaranteed to have the start and the end value, and the step also will be guaranteed no matter how much hard it is for it to actually divide it evenly, right? So what I mean by that is, for example, if you see here, mp.range, arange, let's say you want to start from 0 and end at 10, and you want to like have a step of 2. So 0 will be included, so it's part of the created array. It steps 2 steps forward until it reaches 8. It knows the next one is going to be 10, so it will not include it. So this is an exclusive array when you generate it this way. However, when you use linspace, right? Linspace is quite different actually. You don't have to give it the step itself. It will actually know like the step, it will calculate it based on the start and stop values that you give it, right? What you have to give it is the start and stop and the number. So if you want 6 positions, starting from 0 to 10, then it will list out 0, 2, 4, 6, 8, and 10. So this is 6, right? If you want 5, this will be quite different. So we can maybe like add one cell here just to check. Okay, so I believe I have NP, right? Yeah, we did actually run that. So let's do np dot linspace. Let's start from 0 to 10 and 6. So if we run this, so you get 0, 2, 4, 6, 8, and 10. If you want 5, so it will even this out also, right? So if you press play, then you have 0. If you only want 5, right? So 0, and the difference between these two, as you can see, it's only 2.5, right? 2.5 to 5 is 2.5. 5 to 7.5, it's also 2.5. 7.5 to 10 is also 2.5. So if you want also maybe like, let's say 11 here, and let's say you want 6, the spacing is going to be like this, right? 2.2 is going to be the spacing. Yeah, so I think you get the idea, right? All right, but it's not going to be the case for arange because you have to also provide it with the step count that you want. All right, let's move on. All right, so creating it with mp.array. So like here, for example, in this example here, let's say we're creating a scores array, numpy array that is, out of a Python list. It's very straightforward. For mp.array, you give it this array. And then after this, I think since this point, you might be like experiencing slow, slow computing until you get this data actually, because it's going to be a Python list, right? This is going to be a Python list where every number is going to be an object, right? Previously, if you remember, we talked about like what's going to be included in each one of these numbers. It's not just going to be a simple number, but it is going to be an object. So until you reach this point of creating a NumPy array, everything is going to be comparatively slow, right? You wouldn't notice it for small data sets, but you would when the data set actually gets bigger and bigger. Right. So for this, um, as you remember previously here, we talked about the attributes, right? The D type, the shape, the dimension, and the size of an ND array, right? So here we can actually see the type of the array, right? So we're expecting an integer, a 64-bit integer, to be generated when we create this, right? So by default, it's going to take these numbers because it is an integer in Python also, then it's going to create an integer for us in NumPy as well. So there are two prints here. So scores is this one, straightforward. The D type is integer 64-bit. Okay, and then for creating zeros, right, of shape 5, you have 5 arrays with 0 set for each one of those elements, right? And then if you want to have ones instead, you can also create ones like this. Yeah. Awesome. I hope everything is clear on this until this point. We might want to come back to this later on. But if you have any questions, I'll be on the lookout on the Q&A as well as on the chat, okay? All right. All right. So let's move on to this section here. So here what we're trying to do is basically like comparing these two linspace and A range, right? So A range is kind of an NumPy version of range of the Python range function. So it returns an ND array, and the stock value is always excluded, as we said before, right? So same rules as range, basically. So in Python, range also works this way, right? So it works with floats as well, right? And linspace is actually different. So here, number of points you want. So you specify them, the number of points that you want, and not the step size. The step size is going to be determined by linspace method itself. So both endpoints will be included, and NumPy calculates the size automatically on the background. So for an A range created array, you have a step of 2 from 0 to 20. 20 will not be included, but 0 will be included. And you will see the result here, right? Evens. The length of which you can just calculate it by len like this, just the same as you do it in Python, right? It's the same thing. In linspace, it's quite different. So you want to start from 0 to 10 here. Sorry, 100. The step count is going to be 11, in which case it's quite easy. So it starts with 0. It guarantees that it will give you 100 as the last element, but the step size is going to be determined by it itself, right? So that's what you get here. And you can actually calculate the step of an array that was created using linspace by just comparing two of the first two elements, right? As you can see here. Temps at 1 minus temps at 0. So these are indices. So if you calculate this one, since it's guaranteed that every step is going to be the same, then the value that you get from this is actually easy, right? So here the step count is 10. All right. So I hope this one is clear, right? So even though you don't actually give it a step count for linspace, you can actually calculate it if you want to by just choosing the first two consecutive elements that were created in that array. So, and be assured that the rest of the gap is going to be the same all the way, all right? Cool, okay. Okay, shape and data type. So we saw these earlier. So we have these types of data types. They're quite important to understand because you're going to be working with SQL databases and the Python programming language and also NumPy and Pandas. So understanding the data types and like what size that they have and what limitations you might encounter because of them is also a good learning step. So let's go over these ones. So NumPy arrays are homogeneous. So every element has the same type. So if you have like an array of floating point, then everything is going to be an array of floating point. So the description is 64-bit floating point, and memory per element is going to be 8 bytes, right? So 8 bytes, 64 bits, 8 bytes, okay? It's going to be the same for integers, 8 bytes, which means like you can calculate like the maximum, the minimum values for this. So these actually include these are signed integers. They're not unsigned. So what that means is they also include negative numbers. So if they're unsigned, then it would mean only positive integers, right? So it would include both negative and positive. Int32 means 32-bit signed integer. What that means is it's 4 byte on your memory. It's smaller, and the maximum number that you can store in a 32-bit integer is actually small. So you can see like the size of those. So let's see, 64 bits integer max value. So for a 64-bit integer, if it's signed, which means it contains both negative and positive numbers, then the maximum value, as you can see, it's this much. It's very big, right? If it's unsigned, it's even going to be double this one because the negative part is not going to be included, which means it will include it into the positive side, and you have a double value of this. So this ranges from minus however number this is, however much it is, and to the positive side like this. And if it's unsigned like this one, so don't worry about the languages. It says Java and C#, but bit sizes are similar in most old languages, Java, C#, C even, which NumPy is written off of, right? So it's the same. So as you can see, it's 18. It starts with 18. So you have the maximum value this way. And for 32-bit integer limit, that's going to be this number. It seems smaller, but it's actually big. It's the biggest cap is going to be 2 billion for the positive side, and for the negative side, it's going to be minus 2 billion, right? For the signed ones. If it's unsigned, it's going to be 4 billion. All right, cool. And you have Boolean values, which only take only 1 byte of memory data, memory area, and an object also. So this is going to be a Python object, in which case the memory size is going to be variable. You wouldn't know the memory size because it's an object. An object can store multiple elements inside of it, and when doing so, the size can increase or decrease without knowing, right? So these are the data types. Okay, so choosing the data type matters at scale because if you have 100 million rows, if you multiply that with the floating point value, which is 8 bytes, right? So what happens is it will take about 800 megabytes of your memory, your RAM, right? So the same size, 100 million rows, for a 32 bits integer, instead that would be 400 megabytes, right? So this, like, if it goes more bigger and bigger, then like you have to have this way of like choosing which type of data type to choose to create those arrays, right? So 100 million rows is actually very big, but like notice like it's not even hitting 1 gigabyte, but it can grow if more than that, go to like a billion rows. It could go to like multiple billion rows, in which case this can exceed to like more than a gigabyte of RAM to store your data. Now, if you have an older version or you're using a server that has maybe let's say a VPS, you purchased a VPS, let's say, and it has only like 2 GB of size, some of that memory area is going to be used by the operating system itself to host itself, in which case you have only like 1.3 or 1.4 gigabytes of memory area to use for your own applications, right? So if you already take 800 megabytes, then that's going to be hard, right? So you're going to hit that cap already. So just taking note of this is going to be important. Right, so shape is a Python tuple of integers. So for 1D, you'd get a tuple like this, and the shape of the value will be returned for you for a NumPy array, right? So if you maybe like create, actually we'll see it later on, but the shape will, in this example, we'll see it, right? So for a 2D NumPy array, you have 3 and 4. For a 3D, you have 2, 3, 4. These are like, you can think of them like X, Y, Z, but these are actually just the layers or the matrix layers, right? So when it gets more than like a 4D and 5D, it becomes very difficult to understand it, like visualize it in your mind. So 1, 2, and 3 are enough. So this is kind of like, think of a cube, right? It has a height, a width, and a length, right? For 2D, think of like a paper. For 1D, just like one line, right? So that's, yeah, these are the shapes. And the shapes are going to be returned to you as tuples, right? Okay, so here we're creating a NumPy array using a Python list, right? And then we're trying to see like the data type, the shape, the dimension, and the size. So if we execute this, so the array itself is this one, right? Straightforward. The data type, as you can see, because we gave it a floating point value that's coming from Python, it gave it a floating point of 64. The shape is going to be 10 because we have 10 elements in here, but it's going to be of type Python tuple. Okay, it's kind of like a list, but it's a little bit different than a list, right? And the dimension, it's a straight 1D array, so it's going to be 1, and the size is going to be 10, right? Right. So if we had a two-dimensional array here, the shape would be, let's say we have, I don't know, we can add more here. Let's add more. Let's delete these ones and let's do this. Add no, add this one and tab, and then add a comma here. Let me copy this line and put it on the next line here. So yeah, effectively what I just created here is a two-dimensional array, right? So it's kind of like a matrix view. So it's the same data, it doesn't matter. But if we try to see the outcome of this execution, the array itself is listed here, still floating point, but the shape is different, right? We have now 2 rows, right? 2 rows, one is this one, the second one is this one, and 10 columns. Well, you can count them and it's actually 10. The dimension now changed to 2, right? Because we have two-dimensional array, because it's a nested list, as you can see. And a list of a list, that's what we just generated here, right? If we generated a list of a list only, that's a 2D array. If we generate a list of a list of a list, then that's going to be 3-dimensional, which is quite complicating. So that's the dimension. And the size, as you can see, it's 20. Well, that means the total number of elements that we have in this array, regardless of which row or column they are. In which case, just count all of these numbers and gives us the size, right? So this is how you can also calculate how much of memory that you're going to be using. We know that here it's a floating point, it's a 64-bit floating point, right? So we can just see size in memory. This is going to be in bytes, of course. That's going to be pages.size multiplied by 8. Right? So in my memory, I'm going to be using, if I'm creating this array, it's going to be 160 bytes. It's much less, actually, it's not even a kilobyte, but this is a very small data set, as you can see, right? Awesome, awesome. Right. Okay, now we just saw them, but we can go over the 2D arrays. All right, so you can create 2D arrays using array itself, right? The same way I showed you earlier. These are going to be the rows, right? Here it's a ticket data. So it's going to be the passengers and the columns, right? So that, sorry, the age and the fare, how much it is, right? This is the fare, this is going to be the age. So row 0 is index 0, row 1, row 2, row 3. So it's 0-based indexing. Again, in NumPy arrays, you have to use 0 as the first element. The last one is going to be 1 less than the size, sorry, 1 less than the row count of your 2D array, right? And you can calculate the shape, the dimension, the size, and the data type here as well. Cool. I think we already went through this in the previous exam, so we don't have to see it again. Excuse me. Okay, indexing and slicing. This is what you know in Python. However, it's a little bit different here also, because you have also like 2D arrays, and there's a little bit of a difference between NumPy and Python. So let's just maybe like take a closer look at indexing and slicing. So NumPy uses kind of like the same start, stop, and step slicing syntax as Python strings and lists. It extends the multiple dimensions with a comma separator, so it's not the same as Python when it comes to multiple dimensions. If it's a simple 2D array, then the way you index it using is the row selector is going to be the first one, and the column selector the second one, the same way that you create a two-dimensional array, by the way. But the enclosure is going to be kind of like these square brackets, right? So for the 1D, what are the rules of indexing and slicing? So if it's just a simple one-line array, it's the same as Python. So the 0 gives you the first element, -1 gives you the last element, right? It's quite different than other programming languages, Python. It's confusing for most people when they start it, because if they're coming from a different language, -1 would give an error actually, because there is no -1, right? But Python uses like a reverse. When you use minus, it thinks like you have to start from the reverse side of the array, in which case it doesn't give you any error, it gives you the last element instead. And it actually goes from all the way down to the length of the elements itself, right? So if you have like an array of 5 elements, -5 would give you the first element, right? As would 0 would give you that element, right? All right, so now slicing. So 2 and 5, array of 2 and 5. So you have a colon here, in which case the index 2, 3, and 4 would be returned. However, it would not include the last element, which is the 5th index, right? So the second element, the third element, and sorry, the second indexed element to the fourth element, indexed element would be returned, but the 5th indexed element would not be returned, even though it's actually here. It's the same as Python, by the way. It's quite confusing though. All right, I see somebody asking why multiply by 8. I'm guessing that's coming from the previous example I showed you guys here, right? So if you remember, when we tried to calculate the size of 100 million, right? 100 million rows, in our memory, if we store it in floating point, like a 64-bit floating point, as you can see here, um, the size is actually 8 bytes, right? For 64-bit floating point numbers, right? Now, so if you multiply that, it becomes like 800 megabytes in your memory, right? Because it's a million rows, you have million bytes. That's how I interpret it. The reason that I multiplied the size here with 8 is because what we have already is like 20 right here. The first one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the first row has 10 elements inside. The second row has the same duplicate, which is 10 again. So we have 20 in total, 20 points, right? These have to be stored somewhere, right, in your memory, which means they will consume memory area. In our case, since we know that it's a floating point integer, more specifically a 64-bit, that means each one of those elements or numbers would need 8 bytes to live in my memory, right? So I just multiply that 8 value with 20 to give me the size, right? So here, what I get is, I think I can also make it a little bit more descriptive here by adding an F string. So F string, so size in memory is going to be equal to this, I'd say bytes, right? So as you can see, it says 160 bytes. This was a lot of space here. Great. I hope that makes sense. Nelly. I think Nelly was the one who asked the question. All right, all right. Now going back to the indexing example, right? So 2 to 5, we're going to be seeing this a little bit more in detail. So don't worry about it. So yeah, 2, 3, and 4, but number 5 would not be included in this slice. The next one is slicing it this way. This would give you every second element in your array. So if you have 1, 2, 3, 4, 5, the elements that you would expect to get if you run this is going to be 2, 4, and then that's it, right? The last element would not be returned. So if you use this though, so you're using a -1, that's not the step, but what it tells NumPy is we want a reversed array, right? So it just reverses our array and gives us that reversed array instead. Array 1 with a single colon and nothing else after that, this everything from index 1 onwards. So everything else after index 1, which means index 0 would not be included in this array, right? And the last one, this one, so array colon 3, we don't have the first one here, right? So colon 3 means the first 3 elements, right? So the first 0, index 1, and index 2 would be returned, but index 3 would not be included because of the same reason we saw earlier, which is this part, right? We only didn't have this number here, but the last one would not always be included, okay? So that's the difference. In the 2D array part, so the syntax is going to be like this. Array of 0 returns the first row. The entire 1D array is going to be returned. Array 0 and 1, row and column selection. This is basically we're choosing the first row, and from that first row, we're choosing the first column. So row 0 and column 1, it says it's a scalar. Scalar means just the value itself stored in that cell, right? So with the previous example, if we chose 0 and 1 in this 2D array, so the 0 indexed row is going to be this one, right? So that's the first. And column 1, right? If it's column 1, within this array itself, we have to choose this second element because indexes start with 0, right? So this is 0, this is number 1. So the number 7.25 would be returned. That's why it says scalar, okay? So if you guys remember your math classes in school, there are things called scalar and vector It's coming from there, okay? But don't worry about it. It's just, you can think of it like a number or the value stored in there. The next one is colon with a comma and a 1. So the first one, it denotes the row, obviously, right? But it's slightly different, right? And the second one, it denotes the column. So what this means is all the rows, I don't want to choose one, I want all the rows, but from all those rows, I want only column 1 to be returned for me, all right? So all rows, column 1, well, what you get is basically a one-dimensional array. How so? So as an example, if we go back here, let's repeat that same one down here. So let's print ticket data. I'm going to choose this one, right? So column for the row, and then first column for the second one, right? So if we print this one, what we would get is the following array, right? It's an array itself. It's a one-dimensional array extracted from this two-dimensional array. But what we got is this vertical bar here, right? So 7.25, 71.28, 7.92, as you can see, all of them until we reach 13, right? So what we meant here was, I don't want to choose any row. I want every row, right? Don't make me choose. Instead, I want to choose the columns though. But for the columns, I want the first indexed column. So just return that. Well, it did return that for us, but it's going to be a one-dimensional array when it gets returned. Okay, going forward to the next one, which is array 0 and 3. Who can tell me this one? It's actually straightforward. You can read it from here, but I just want to see like if everybody is on board. So array, this one actually, 0:3. What do you think it does? So you can use the chat to answer that. Maybe a little bit more descriptive than this line right here. Anyone want to try? Yeah, go ahead. On a read day, I think that's the name, right? Okay. I don't think I'm hearing you, though. You can maybe like answer it on the chat. So I'm just gonna mute you back. All right, yeah. So the first 3 rows, yeah, that's the answer, of course, but I wanted it to be a little bit more descriptive. Like why is it only like the first 3 rows? Why do you think it is? Use the chat to answer that. So array 0:3. It looks a little bit slightly similar to this one, right? 2 and 5, but this is for 1D array. When we use it in 2D array, it's quite different.
Can you hear me?
Specified. On a real day. Okay.
Can you hear me?
Yeah, we can hear you. I can hear you now.
Okay, so it says from 0 to index 3. So so the third index there would not be added. So it would just be index 0, index 1, and index 2. So there's no comma to specify column. So it's all columns, but the first 3 rows, that's index 0, index 1, and index 2. I'm not going to include index 3 there.
Exactly. Yeah, thank you for that. Yeah. So yeah, the last one, the last number in this column separation will not be included most of the time, right? So first three rows, starting with 0, and I end up at 3. It's the same as the previous one, if you remember, right? For the 1D one array. It's kind of the same, but here, since it's a two-dimensional, if we have something else after that, after a comma, it becomes different, right? But if you only have this one, it's quite similar to the 1D version, right? So the first three rows would be returned, but I don't care. Just give me all the columns, right? What that interprets into is, so the first three rows would be returned. So 1, 2, and 3 would be returned for me. But the column, so I didn't provide any column, right? So these are the three that I expect. So it's going to be a two-dimensional array again. So just to demonstrate, so 0 to 3, if I made it this way, this last part is our response. As you can see, 22 up to 7.97, right? This diagonal, right? So I didn't care about the columns, so I got every columns. And also note that this type of sorry, double click it. This type of annotation is the same as doing it this way, right? 0 to 3, comma, with only one column, right? The same as the previous one. Here, we didn't care about how many rows returned. I want all of them. But here, we cared about how many rows are returned. The reason that we're not doing this same type of annotation above right here is because we always have to start with a row, right? We have to start with a row. So if we, I don't know, if we did this, if we wanted to do this one, sorry, this way, it wouldn't work, right? It wouldn't work that way. So we always have to give, if we want every row, we have to say column first, and then however many columns that we want, right, after that. It's quite hard to differentiate between colon and column, actually, when I'm saying it, but that's okay. Okay, so the next one is array from 0 to 3. That's for the row. And we're choosing column 1, right? We're specifying what column we want here. So 0 to 3 would be returned, but column 1, which is index 1, which is the last index in our array here, would be returned. So what we will be expecting is only this column right here returned as a one-dimensional array, okay? So just to make sure, you can add comma 1 here and run this. This is a one-dimensional array, as you can see. The previous one was not a one-dimensional array, if you remember, right? This is a 2D array, right? And the last one here is slicing using column 2 and for the row and column 2 for the column. And so this gives us the top left 2 by 2 submatrix. So if you we'll see this one. So this is going to be from the beginning to 2 for the rows, and again for the beginning to 2 for the columns. So the top left side, right? So I think for you it's going to be top, I'm not sure, this way, I don't know. So the top left side means the side that you are starting to type, right? From this side. From this side, the 2 by 2 matrix would be returned for us, right? In our case here, yeah, we can use it, I think. Let's try it out. 2 here as well. Yeah, we can use it because this is included, all right? Okay, so these two are actually included. And the top left corner of our 2 by 2 matrix was returned, which is basically, in our case, if we had more columns here, they would not be included in this, but already we have like only 2 of them, so that's what gets returned, right? All right. Okay, so 1D examples are these ones. Maybe I'll share with you guys on the slicing, or maybe like this workbook itself, maybe like I'll share it with you later on so that you can work on it. Okay. So 2D indexing, just a little bit deeper here. We're actually creating, we have ages. So ages is already, so let's just run it. So at 0, this is for the 1D. So let's go to the second one actually here. It's for the 2D. Yeah, we already have it, like the ticket data at 0. So first passenger is going to be this first row, right? Row 0 and column 0. This is what gets returned, the number itself, not the array. Row 0 and column 1, that's the fare. So just to remind you guys of this, tickets is this 2D array, right? So the first row is the age of the custom, and the second row is the fare or the price, right? So if we go back here, row 0 and column 1 would get you the fare, 7.5, right? The next one is all the rows, all the rows with only column 0 returned, which is the first column of that. So that's returned. So all fares, so that means all ages, right? So all fares with only, this is going to be column 1. That's how it gets returned. The first 3 passengers, you can return it through 0 to 3 like this. In the top left 2 by 2 corner, you return it this way. So you use like this 2 by 2 matrix return. So this is the top left side. All right. Okay, Boolean indexing. So in Boolean indexing, so this is basically, we're going into like the filtering phase. Yeah, so this is the filtering phase of arrays. So Boolean indexing is one of NumPy's most powerful features. So you can use Boolean values to be able to like filter your array, right? You can use, it's a very easy syntax if you see it. It might feel complex when you read about it, but when you see the syntax itself, it's very easy. So it's like exact same mechanism that powers Panda's row filtering method. So mastering this here and going to Pandas. Yeah, going to Pandas is going to be very trivial. So just understanding this is the first way. So step 1. So let's create a Boolean mask. Boolean mask means we can use some kind of an expression to be able to create a separate array from the array that we already have, right? So this applies. So maybe like an age less than 18. We already have like, let's say, an array of ages like this. And we can create a mask, a Boolean mask off of that. And then later on, filter it based on this Boolean mask, right? Okay. So based on this expression, the array that we create off of it is going to look like this. 22 is obviously less than 18, so we get a false value for the first element. For the second, also the same, third, but the last 2 are less than 18, so we get true values, right? Straightforward. Now this is our mask. Okay, let's go ahead and use this to actually filter. Well, it's very straightforward. What you do is, for age, you use as if like you're going to be choosing a specific element out of it, but what you give it is the mask. In which case, NumPy is actually smart enough to know that it should return only the positions in the mask that have, or only the positions in the ages array that the mask is saying are true for the expression that it got, right? So in which case, ages at mask, everything that aligns with the false values will be omitted, and everything that matches with the true values will be returned, in which case we have only like 2 and 14, right? So how do you actually create this? Well, you can use conditionals. So there are 2 ways of using conditionals here. So you can use maybe like a single ampersand sign to combine two things maybe, and an or sign or the vertical bar in your keyboard to mix again, right? So these two can actually be used to mix two two expressions, right? But if you have only like, let's say, ages less than 18, then you don't need these combinations, right? So let's see this in action. Maybe I think the first one would be great, but this yeah, this workbook doesn't have one. So let's create one more um, cell here just to work on this, right? So let's pick up these ages. Actually, I have to create them. So I'm just going to copy this and say ages will be np.array array and give this file, right? Okay, we just created a numpy array. Now let's create a mask off of this. So the mask is going to be equal to, well, now it's important to know like how to create a mask, right? So the way you do that is, well, it's alluded to it here in the combination part, but what you do is ages, and you give it some kind of an expression in square brackets like this, right? So let's say ages less than 18, right? Okay, we just created the mask here, right? So what this means is we have created false, 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 true, true array. So just to make sure that that's correct. No, sorry. That's not the mask. This is actually the array. Okay, I moved one step forward. We have to create the mask here. So the mask is going to be only the expression. So that's going to be the mask. All right, sorry. So this is, so it's quite interesting, right? So you have an array, you use a greater than or less than sign, a comparison in this case, just to be able to create a Boolean array, basically. And if you're worried about the performance, don't worry about it, because each one of these values, like the false and the true values, each one of them just only cost 1 byte. If you remember from our previous encounter of like the data types, Boolean values only have like 1 byte, right? So if you have 1 million rows, you'd only create 1 million or 1 megabyte size of array, a Boolean array, right? And 1 megabyte for 1 million rows is very small, right? So the performance value of it is just so great. Now we can use this mask itself to be able to create a filtered value, right, based on this mask. All right, straightforward, right? So 2 and 4 is the only elements that are greater than 18. So that's the one that we return here. All right, so how about we combine them this way? How about we want elements in the array that are above 10 and less than 30? So if we just manually read through it, above 10, we have 1, 14, 2, 26, yeah, 38 as well, and 22, right? We have 4 of them. But we have to satisfy also less than 30, in which case we have to drop 38, right? Now that means like we have only 3 elements to be returned. So for that, the way you create the mask is using the ampersand. This is quite different from Python, right? In Python, the way this is actually an AND operator, right? But in Python, you would use just AND, a simple AND, right? But it's quite different for NumPy. You'll use an ampersand like this and say age less than 30. So let's fix this one. This has to be greater than 10 as well. All right. Okay, so this is the mask. So if we print out the mask, oh, okay, we have syntax error. It's good to actually read the syntax error most of the time because you have to understand why this is happening. So it says a value error, the truth value of an array with more than one element is ambiguous. So use any and all. So I'll not be using any or all. What this tells me is it's kind of like combining all of these things and it's actually confused. So what I have to do is I have to use parentheses to separate the two expressions, in which case it's easier for it, right? So the first one has to be satisfied, but also the second one has to be satisfied as well. In which case, for the first element satisfies both cases, so that's true. The second 38 doesn't because it's greater than 30. The third satisfies it, so it's true. The next one is false, which is for 2 because it doesn't satisfy greater than 10, and 14 actually satisfies it, right? So based off of this, you can create a just filter with mask. So you have 22, 26, and 14. You can use the OR operator here, which is the vertical bar. So it had what this means is it's quite actually like confusing sometimes, but you have to read through it by like reading it out loud is much more better to do it that way. So if we use OR operator, what this means is elements in ages array, they have to be greater than 10, or they have to be less than 30, right? If they're not both, then if they're not both, then the value will be false, right? In our case, let's start from the first one. So does this satisfy our argument here? So age greater than 10, the first one, yeah, it does, right? So if it does, then it's going to be part of the mask. It's going to be set to true. 38, it's still again like greater than 10, right? So it satisfies it true. It doesn't even want to go to the next one. If it's a true value, then it doesn't run the second expression. It doesn't have to, because or means, if you guys remember from like maybe your math classes when you were a kid, and or are like, they're like kind of like logic gates, if you remember. Maybe if you may not have taken those courses. So if it's, for example, or, just to give you like what it would be. So true or false would always result in true statement, right? True and true, obviously, that's going to be true here. True or true, that's going to be true as well. False and true doesn't matter, it's associative, right? But the only case where or operators return false is if both of those cases are false, right? So both of these need to be false for some values for them not to be returned, right? In our case, if we just run this mask, what we get is the original array again, because every element satisfies at least one of these conditions, right? So let's try to find maybe like something that can filter out the number. So it has to be greater than 10. That wouldn't work with 2, right? So let's fix this second one just to be able to like not include 2 in here. Easily what I can do here is I can say ages equal to what exactly? What should I give it here? Let me ask this question. So the goal here is to not have 2 as part of the resulting filter, if that makes sense. Okay. So what should I probably do here? It could be equal to something or not equal to something. What should I do here? You can use the chat again. Anyone? gonna try. So the idea is I don't want 2 to be part of the resulting filtered array. Age is equals 14. Okay. Mary Jane says age is equal to 14. The problem with that is if I made this equal to 14, would that work? Let's go through it. It might actually, right? So 10, it's greater than 10, true. This is true, this is true. This is false for the first one, so it would go to the second case here. If it goes to the second case and ages is equal to 14 is not true, then it would return false, right? So both cases become false for 14. So anything I put here equal to here, anything I put here which doesn't include 2, right? Which makes this 2 like falsy value for when it comes to 2, then it works, right? It would just work. So if we just execute this, sorry, I don't have to do like comparison type, not equal. So 2 will be omitted from here, right? So we satisfied this last line right here. That's the reason. So and using the AND operator is quite easy actually, but the OR operator, you have to think of it just a little bit further, okay? Yeah, use not to. Not to also can work, like not equal to. 2 will also work, right? That would work. Yeah, most of you guys got it. Awesome. Okay, so let's move on to the next one. So single condition Boolean indexing. Give me a second. All right. Yeah. Okay, cool. Right, I think we might have to like move a little bit quicker on these ones. But if you guys want to exercise these things, it does have more description, this notebook. I'll let the guys know and the gals know about like how to share this maybe later on. We share it on eHub or somewhere. Yeah, so single condition Boolean indexing, combining those two, we just saw these ones. Boolean indexing on 2D arrays, filtered rows. Yeah, so we can see these ones as well. Appending and deleting elements. So I think this is quite nice. So let's maybe skip these lines and go on to appending and deleting elements. All right. Okay. Felix, yes, I'll be sharing that. No worries. Okay, so the most important thing to know, NumPy arrays have a fixed size of memory, right? So, sorry, there's a car around. Sorry for that noise. So unlike Python lists, so Pythons, you can just simply increase the size of your list very easily. What you have to do is just have list.append, and it's handled for you very straightforward, right? So, but when it comes to NumPy arrays, since it's going to be using the underlying technology is C, C does not allow you to add more stuff. Like natively, it doesn't allow you to add more stuff on a generated simple array. There are like resizable arrays in C, of course, but the underlying, like the main arrays themselves that you create, the simple arrays in C, you cannot actually expand them. You would have to create a new one and then copy all the elements that you have. And that new one has to be like 2 times or 3 times bigger in size when you allocate it first, right? So NumPy arrays occupy a contiguous block of memory. So they're side by side, as I mentioned earlier. To add or remove elements, you must allocate an entirely new array, okay? So That's why mp.append and mp.delete, both of them, they return new arrays, right? So new arrays means a different place in memory will be allocated first, and all of that value that you have in the old array has to be copied over, right? So they basically do not modify the original array. So effectively, what you're creating is when you try to append new elements in, then that would just maybe just create a simple array with double the size or 3 times the size, okay? So mp.append, so you have to provide it with the array, with your older array, and then the values that you want to provide, right? So what this does is it concatenates these two. It returns a new 1D array without an access argument. And mp.append, it flattens the 1D array first. And for 2D work, always you have to specify the access to be able to like do this, right? Okay, so what's this? So for example, for mp.delete, you have the object, the axis. So axis 0 and 1, what are they exactly? So mp.delete, right? So the object. So this is the index or list of indices or slice to remove, right? And the axis equals none is going to be flattening the 1D. It's going to be flattening to 1D, and then it deletes those elements, usually not what you want for the 2D case, right? So what are the axes though? So axis 0, this deletes rows, right? So array gets shorter vertically. So if you have more rows, then it removes the extra rows that you don't want, that those you want to delete. If it's axis 0, I mean, if axis is equal to 1, then that would be column deletion, right? So the entire column would be deleted, which means internally it would have to loop through each of those rows and remove the last element and replace all of those rows, because it's a 2D array, with a new array, and then those pointers are going to be added in. Don't worry about that, like those details, because they're going to be handled by NumPy themselves. Okay, let's see, append. So for example, we do have ages from our previous encounter, right? Okay, so the length of it is, you can calculate it this way. It's like Python. Okay, now let's say what we want to do now is append 2 more ages. Ages, by the way, is just a one-dimensional array, if you remember from our previous run, right? So if you append it this way, so append 2 new ages, right? And since the ages, the old array itself is not going to be affected, what it does is it will concatenate these two and then create for us a new array. So we have to capture that in some kind of a variable, right? So age is updated, gets the value of np.update, right? And then when you run that, then you can see like the length later on. So the original array is this one. The length is 5. After concatenation or appending, we added the last 2 elements, and take note of that also. They're going to be added as the last 2 elements, right? And now the length is this much, right? This is for 1D, right? For delete, so 1D remove by index. So the deletion, this also gives you a different array. So you have to capture that array also again. So you have to give it the old array that you want to delete from and the indices, right? So this removes the elements at index 0 and at index 1, sorry, at index 2, and it returns a new array, and the original array is going to stay intact. So the first array is not going to be deleted, or it's not going to be affected. So you can delete a single element if you want to this way, not giving it an array, just give it the number or the index. Multiple arrays by index list, or what you can do is you can give it a slice so that it can start from index 2 up until index 4, not including 5 to be removed, right? So this is, you know, it grows from the previous encounters that you have of slicing, right? It's the same thing. So let's see an example. Ages removed. So we do already have ages, right? It has not been updated because we returned a new array. If you remember from the previous one, a new array was saved here and ages is not actually touched. So we want to remove here from ages 0 and 2. So the original array is going to be this one, ages removed, and the length. So let's see the size now. So the original array is the same, and we removed 0 and 2. So 22 and 26 were removed. So we have 38, 2, and 14. All right. How about in 2D? This is important that we have to go through it. That's why. Using axis to delete basically like the rows and columns, right? Axis. So what does it mean exactly? So axis 0 means delete across the row axis. So a row actually disappears. So think of 0 as like the row and columns as the as 1, right? So this means delete across the column axis. That means the column disappears. So think of it as if like when axis shrinks after the operation, axis equal to 0. This means row shrink. You just deleted a row. Axis equal to 1. Column shrink. You just deleted the column. Okay. So 1 for column, 0 for rows when you use axis. So after deleting row 0 from, let's say, 10 and 20 array, you get 9 and 2. So this is the sizes, right? So the size, let's say, is you have 10 rows and 2 columns. After deleting row 0 or the first row, what you get is 9 rows and 2 columns, right? And then after deleting one row from, again, 10 and 10 columns, sorry, 10 rows and 2 columns, then what you get is 10 rows, but 1 column is gone. So you have only 1 column here. So let's see. The ticket data, if you remember, there are 2 columns and 10 rows, right? So if you want to delete, for example, from the ticket data, the second argument is going to be what you want to delete. And if you say axis 0, then that means the first row, right? 0 goes for row. So the first row is going to be gone. So that will return. So the deleted row is going to be row 0. So you'll see that. So the size would be 9 and 2, right? So again, what you have to understand is delete also returns a new array. So you have to capture that into a new variable, but the old ticket data is going to stay intact, right? After deleting one row, you should see this. And after, if you want to delete a column, in this case, the second column, right? Or the index 1 column, you have to give it access of 1. So if you run this, so our original ticket data, the shape is 10 by 2. After deleting a row 0, you have 9 and 2. After deleting a column at 1, you have 10 and 1, right? So the result, just the ages, which means the result here is ages only, which means the deleted value is included. So if you remember, the tickets data was ages, the first column, and then the fares as the second column, right? Now, when I said 1, index 1 was removed from the column. Index 1 was the fare, right? Now we only have the ages column, so that's what gets returned here, right? It might be quite complicated, but the one thing that you don't have to forget is all of these operations, like deletions, appendtions, all of them, they create a new array. So always do not forget that you have to save the output of delete and append to a new type of variable so that you can capture it, and then that's your new array, right? And then after that, what you can do is if you don't want the new, if you don't want the old array, what you can do is just say del tickets data. right? So the old data, the data would be gone like this, right? Otherwise, it will stay in your memory. So you have to take note of all those things. All right, I think we have like 15 minutes. All right, so let's talk about aggregation a little bit quicker here as well. So aggregations. So these are like specialized methods that you use to compress your, it could be like a 2D data, or it could also be 1D, to give you like a centralized and 1D value for maybe like it could be the average of each of the rows or the average of each of those columns, right? Or the mean and the max, the standard deviations, all of that, right? So you have these available in NumPy. So the sum would give you the sum of all elements. The mean would give you the arithmetic average. The mean and the max would give you the smallest and the biggest value. STD would give you standard deviation, and the like, right? But it matters on which axis you want to do these aggregations. Okay, so the axis parameter collapsing a dimension, right? So for example, if you have a 2D array, let's say this 2D array, you have column 0, column 1, rows 1, 0 and 1, 0, 1 and 2. You have three rows, right? And two columns. Now, axis 0, if you use axis 0, then that means it will collapse the row itself, right? That will collapse the row itself. Dimension. I think I see someone raising their hand. If you have any question, maybe like raise it on the Q&A. I'm looking at that side, but I don't see any questions there. Okay, so if you have any questions, just put it there. All right. So axis 0 means collapsing it, collapse the row dimension, right? So one result per column you would get instead of like the full row. So the rows actually disappear, and what you get is one value for that row itself. So axis 0 collapses it in row wise like this. Axis 1 collapses it in column wise, and then gives you either the sum, the mean of those collapsed values. When I say collapse, it's like aggregate what I mean, right? So axis 0 would give you, for example, for this one, if you want to calculate something, doesn't matter which one it is, if you want to calculate something, it would use all of these values to aggregate and give you the result, right? That way. So that means you have like one column only. If it's axis 1, it would collapse all, for example, for this first column, you would get only like one value for one column. So column-wise collapse would happen, and you'd have like two values for each one of those columns, right? So all the columns values would go, and you have like two concrete scalar values. Okay. Okay, so 1D aggregations. So for 1D aggregations, it's very straightforward. You just compress it in one direction, right? So for ages, you can have like the sum of them. What this means is you're trying to extract like the sum, but also you want to have a 1 decimal point, how do you say it? 1 decimal point precision when you have an output, right? These all things mean that. So for the mean value, for the median value, for the mean max, the standard deviation, everything, you can calculate it for one dimension. It's very straightforward. You don't need accesses here, right? So if you run this, so the sum is going to be 102. So it's much better to actually see that. Or I can just use ages. Okay, I think I have to print them. Yeah, so for these ages, if you add all of these together, you would get 102. The mean or the average value of this would be like adding it and dividing it by 5. The median is another one. The min, the smallest value, which is 2. The max, the biggest value, the standard deviation, and all of that stuff, right? So it's very straightforward. But for 2D, you have to give it the axis, right? And again, you get a new value, right? So that new value has to be stored in a variable, right? So in which case, for I think I'm using the same data. No, I'm using the ticket data here, right? So if I want to create a mean value, so let me also first print here the ticket data first. So axis 0, as we talked earlier, axis 0 means collapsing it row-wise, right? So all the rows are going to be collapsed into one value. The columns are going to be intact. So um, the mean value for that, for axis 0, we calculated that's column means. So mean or the average. Mean means basically average. The average of the ages is going to be column means at 0 and 2 degrees of precision. Column means at 1, that's going to be for the average of the fares. And then we have another one here, row-wise collapse. So let's run this one. All right. So the original one is this one. The mean age that you have is this one, right? So the mean age. So this is the age. So all the rows are going to go away, right? Everything is going to be added, divided by the number of elements that you have in this, the number of rows that you have, and the average of that is going to be calculated and given for you here. And for the second column as well, you get this one, right? You can also print out the call means. I think I need a new line here. Yeah. So these are the two column means, as you can see, right? So these collapsed and it gave you a value here as well. And axis wise, like when it's 1 also, you get these values. Okay? All right. Any questions until this point, maybe? I think we might need another session for the pandas because I don't think we have time to jump on and finish everything on the pandas side. I do have an example prepared for you guys, as I told you earlier, which is the Titanic data I showed you earlier. This one, and working on this one with pandas and stuff. But I don't think we're gonna have time. But I will definitely make sure maybe like I have a recorded session on that, or I'll talk with the team to see if we can set up another session for pandas. We can make it. All right. Any questions until this point? Okay. Yeah, okay. Felix, yeah. I'll take note of that and I'll share the file with you guys. All right, and also I think we will take a look at these ones. And there's also an exercise here, by the way. I think it's a good resource that I found here, which you can play with. I think there's also solutions for all of them. Just to, keep your mind working into understanding like how NumPy actually works. But this doesn't also only like hold NumPy related questions. It does have like pandas foundations as well, which is nice, right? And we also have here yeah, so the example that we're going to be using in the module 2, which is pandas foundations, was let me see. Yeah, working with data frames, basically this one, we'd be using the Titanic data here. So it's included, so this file itself should suffice for you to use. There's also yeah, this is the Safari Watch. This is a different, um, like it's the same type of exercise that you guys are going to be doing in the example, so the exam that you have on pandas and NumPy. This has a database of its own, Safari Watch. It's kind of like the same look. It has the same look as your project. However, it's different. What it's trying to solve and stuff like that, it's different, right? So it has like geographic zones, climate data, habitat features, and wildlife records. And there are some issues with some of the columns here, which you will have to solve. So I think maybe like a workshop session on this one would be great, right? And this is just a simple foreign key relationship or joint key relationship between the geographic zones and all of these other tables that you have. And then you're going to be working on them. The size of it is about like 3,000 rows. So it's great. Like working on bigger data sizes is going to make you appreciate why you would want to use NumPy and Pandas instead of Python itself or some other type of library, right? So try to find data sets out there. I just found this on Google, right? So GitHub user account and the Titanic.csv, right? You can just Google large CSV data sets and exercise it yourself, right? Use pandas, use NumPy to extract some stuff, to switch things, um, to um, to clean up data as well. There's a cleanup here that we're going to be doing. Most of these data, by the way, as your data scientist, um, you know that AI is trained with the data that they found on the internet, right? Any data that they find, they just scraped that website, or whether that's a PDF file, a text file, a CSV file like this that has been put for everyone. Um, to see, and they just fetched that and trained it for, structured it, cleaned it up, and then used it as a data set for their AI, right? The problem is, like most of the data on the internet is malformed. It either has like weird forms in the way the numbers are written. Maybe like the column was a number, however, the value that's stored inside that column is just a string, which is confusing for a simple program, right? Sometimes you might have like, you might want to, calculate some kind of a mathematics on that. And since it's a string, it messes with everything and you get a very, very different type of result, or the program doesn't work. So you have to clean up that data first. So that's the reason that you need to use pandas and NumPy. Pandas, as I told you, it's built on top of NumPy, right? But it has more functionality, right? So try to find these types of data, especially like find .csv files. I don't recommend using like SQLite files or something that you cannot read as text like this, because there might be some things embedded in them that you don't want in your computer. Maybe, I don't know, some kind of a code or something, right? So there are also black hat people out there in the internet that put these types of data. So just make sure that it's a text value like this, and you can also dump it into an AI to try to see if it's okay, and then use it locally in your Jupyter notebook. Okay. All right. So I'll talk with the team on like if we can actually hold a session on the pandas only, or yeah, if we can do anything else. I believe Isaac, I'm not sure why you're suffering, but we're here to help, okay? Don't fret like this. Yeah, we're here to help. Just reach out to us. We're gonna be helping you, okay? Cool. Mbali, or Saigu, you guys want to take over?
Can you just share the slides?
Sure.
Yeah. All right, everyone. The assessment for this week is the integrated project Understanding Margin in Dogo Agriculture, and it's going to be due next week, Tuesday, on the 18th of March, and the due date is 11:59 GMT. So start working on it now. The recording for this session will be shared with you on the program hub. And yeah, if you have any questions, feel free. Next slide, please. Yeah, if you have any questions, kindly feel free to reach out to us on eHub or FreshDesk or AnswerBase, right? So we'll be meeting same time next week, and yeah, see you next week. And what's the final slide?
Yeah, I think we're good, right?
All right, good. So thank you, everyone, and we look forward to seeing you next week. As I said again, if you have any question or challenge, reach out to us, and we'll definitely have answers to your problems. All right, thank you very much. And Leko, you can play the music.